now. Okay, then let me get started. Hello, everyone. Welcome to our course reading group for diffusion models. It's good to have several of you here and also others online to join me today. So today I'm going to talk about diffusion models for text-to-image generation. This is probably the hottest topic for the past few years. I mean, for in general, research in image or generative models, or like people try to bring text and image together. It's just recently people bring diffusion model into the framework to get better text-to-image generation. So first of all, for some credits, today some of my slides and pictures are taken from these two sources. Like one from University of Central Florida, one is from the CVPR 2022 tutorial. So you're welcome to check the slides for more details. And the outline will be like this. I will first go over these 5 papers, all from OpenAI. Looks a lot, but don't worry, not too much to cover for this. So the last 3 here, starting from guided diffusion and then glide and DALL-E 2, these 3 are like more closely related to what we have been talking about. In other words, they use the diffusion model. The first 2, the CLIP and the DALL-E, they actually do not use any diffusion model. But because this is like a serious work from OpenAI, they keep referring back to CLIP and the DALL-E like all over the place in the last 3 papers. So that's why I'm going to introduce everything in this time order, just starting from ICML 2021 all the way up to, I think DALL-E 2 submitted to this year's NeurIPS, but didn't get accepted. But anyway, I will follow this order, and you will see there are connections between these papers. At the end, I plan to do like a live demo using this disco diffusion model to actually generate some, like maybe I can collect some ideas from the audience of the text prompt, and we can actually generate some videos on our own. Images on our own. We will look into video generation in later reading groups. So before I start, I want to state some of my personal opinions about these 5 papers, because I really spent several days studying them. From research point of view, I feel like for all these OpenAI papers, right, it's probably their research style that the novelty, if you ask me, or those blogs and YouTube videos I watched to help me understand these papers, people seems like all agree on the novelty is not super significant. Basically, they bring some existing ideas together into one framework and just demonstrate, oh, these ideas work, and then they just show their amazing results. In other words, if we're asking about the insight these papers try to communicate, it's actually not very deep. So later on, we will see for all these 5 papers, I probably only need 3 to 5 slides to tell you the main idea about what's going on. So it's very easy to communicate the main idea. Finally, I feel like the paper writings, probably because I'm less familiar with the domain, probably because they keep referring back to some like jargons or like previously used methods. So these papers, they have large dependency on each other. So you really need to read a series of them in order to understand the later ones. Otherwise, they just don't explain what's classifier-free guidance and what's FID score, all of these things. And it can be hard for you to read the paper on your own. So basically, you can think of it as I'm doing you a favor here today, because I really looked at a lot of other resources like blog posts and YouTube videos to help me understand these papers and bring up the main idea here for you. But this is just for research side. Engineering wise, I would say these papers are like very challenging engineering projects. You need a lot of implementation tricks to make things work. For example, we will see that these papers, they usually train on millions or billions the data set. You can face this large scale training challenge. And then in order to improve the performance, you need to tune the architectures and a lot of hyperparameters, a lot of engineering work involved there. And then also you can imagine that you need like huge amount of computational resources to support. So I would say, even though research-wise, we probably say the novelty and insight is not that deep, but the engineering-wise, it is still challenging and meaningful projects. And lastly, maybe business-wise, right? So this is, I guess, if you use social media like Reddit, Twitter, anything, and then in the machine learning community, this is really a big social impact there. So this is just my personal opinions about all these papers we want to cover today. Just before getting into the actual papers, give you some general ideas. So we will talk about these 5 papers. Like I said, each of them will be relatively short, for about 3 to 5 slides. So I feel that's good enough, but definitely interrupt me if you find anything as unclear. We can stop and look into more details. Let's start with the first one, CLEAP. So the full name is called Learning Transferable Visual Models from Natural Language Supervision, right? So this CLEAP model, I would say, right, in my opinion, is just contrastive learning between images and text. If you understand what's contrastive learning, I believe all of you do, then it's pretty straightforward. Right. For this paper, I feel like the main contribution of this paper is that they actually created this data set with 400 million image text pairs. And here is they show the result of training on this big data set. And then after training, they can just do zero-shot learning, which gives reasonable good result. And if they do what they call linear prop, like meaning you use another linear layer at the very end, it can outperform this, say, ResNet 50 or some other like contrastive learning framework we are familiar with, SimClear. So this is basically what's what this paper achieved. But how did the CLEAP paper achieve this? Like very straightforward. Only need one slide here. So basically, they have a lot of image and text pairs, like something like this on the left. And then they just do contrastive learning between these two, meaning they just encode the image to get an image embedding, encode the text and get the text embedding. And then within each mini batch, they will have a lot of image text pairs. They just take this whole matrix, similarity matrix, and maximize the ones of the corresponding image and text, and minimize those ones that are not correspond to each other. So just do contrastive learning on this matrix. Then finally, what they want to get is these 2 encoders, right? So after the training stage, they will say throw everything and just keep these 2 encoders. Then later on, if you want to do like any visual task, you can just take this image encoder to generate a good image embedding for you. Or any language task, you can take this text encoder. We will see several papers in the later stage. They just take these encoders for granted and build up on top of them.
So they're also like false modality transformer.
Mm-hmm.
Then this part can be replaced by that.
So yeah, that's a good question. In this case, because they separated the text and image into 2 different encoders. So I think this text encoder here is just a GPT or like something like the regular language model. So they didn't mix up things. But later on, we will see they actually train. So in one of the later paper or 2 of the later papers, they actually train a transformer where they concatenated the text encoding and the image encoding together, plug them into transformer to compute the attention. So yeah, just at this point, the multimodality haven't been incorporated. Yeah.
What's the year?
This is the ICML 2021. So yeah, we can maybe look at the time again. So the CLEAP ICML 2021, DALL-E about the same time, all in February last year. And then this guided diffusion is NeurIPS 2021, GLIDE is ICML 2022. DALL-E to
Because I
Yeah.
think too, of course, they probably started the project quite earlier,
Yeah.
because the cross modality transformer actually, I think, even earlier.
Okay.
I think it's like
2020. Yeah, you mean like the vision transformer paper? Okay.
the circular respect.
Yeah. Yeah. I also remember like CLEAP came after the vision transformer paper. Yeah. Yeah, it's probably iClear 2020. Yeah. Okay. Then this is the first step, which is contrastive pre-training. So once these two encoders, then basically CLEAP is done. But they tell you something more about what CLEAP can do in this case, right? You can actually use it to do zero-shot image classification. What you do is that you have this image, right? And then there are like a few classes this image may belong to. Let's say it's ImageNet, you have 1,000 classes. What you do is that you just construct a sentence for each class. Say you construct a sentence, say a photo of a plane, a photo of a car, or like other classes. So you have 1,000 different sentences now. Then you just encode your image, encode this 1,000 sentences, and then just compute their similarity. Then you pick the one with the highest value as your classification result. In this case, seems like we are converting a simple classification problem into a more challenging image caption matching problem. But what they showed was actually just doing this kind of zero-shot learning, the CLEAP model can achieve relatively good result, right? So this is what's amazing about this paper. First of all, the data set contribution. Second of all, this zero-shot image classification. Okay, yeah, that's basically the first paper. We will visit it several times in later papers. But any questions about CLEAP at this point?
You just have to find the correct word to fill out this object.
Yeah, so usually for let's say for regular image classification, you just have 1,000 labels, right? So you just have 1,000 classes, and then in this case, for this zero-shot learning, maybe say this is a dog's picture, the correct class is dog, right? And then they just construct a sentence saying a photo of a dog, and find that sentence is has the highest similarity compared to other sentences. Say a photo of a cat, a photo of a plane, or other sentences. This is just you choose to use this sentence. You maybe use other things like a picture of a dog or anything. Intuitively, that should give you a similar result if you use a figure of a dog. But just in this case, they choose a photo of a dog. Yeah.
I still have a question for the technical part. So on the training part, pre-training part, I think it's quite clear. Or you have to make the testing for an easy for the result. But then for the step 2 and step 3, are they just for the inference, or actually they also involve some training?
Oh, this is just for inference. Yeah. Yeah.
So the goal, of course, we try to do the zero-shot prediction for image. So image is still like the main part.
Right.
And then the purpose try to predict that kind of mascot word, that object. So that object is a mask, right?
So in this case, you actually know what the classes are in advance.
So the classes are predefined.
Yeah. Yeah.
Okay. So it becomes a classification. Oh.
Yeah.
With the input, the image part is quite good, or the text part will be the input.
So let's say like at the beginning, you want to classify this image, and there are 1,000 possible classes. These are the input. So take this 1,000 classes. The first thing you do is that you plug each class into this sentence, and then right, and then you have 1,000 sentences. Then you just find the most similar one. Yeah.
Okay.
Yeah. Yeah. Let's see what's going on. So, okay.
Can you just make some comments? Vivian has a question.
Yeah. So yeah, let me read what's going on here. Okay. So I guess for the news comment, first of all, it's saying unimodal encoder is easier to scale up. Second of all, it's saying that unimodal encoder can do zero-shot learning out of distribution solution, right?
Yeah, probably I can explain a little bit. So
Okay.
like as we all know that before CLIP, like as in maybe 2020, we already see lots of visual language model, and most of them follow like the transformer like the BERT architecture that directly fuse like two modality together, and they like somehow train get good results. But the key thing for the CLIP is that they can do a so-called zero-shot learning. For example, or like recently, we many people also call it out of a vocabulary, or like the open vocabulary classification. It means that even without a training set or like a fixed concept set, we can still do the classification for that if we know their like a semantic meaning in language. For example, previously when we do ImageNet, we probably collect, for example, thousands of label and classes and treat each one like with specific ID, for example, ID 0 to ID 10. But via this kind of constructive learning, the way to do classification may be different. We might, if we want to do like a specific classification, we can somehow collect the text, for example, description or like this object name for that and design some prompt to like turn it into a classifier. And then we don't need any like fine tuning and can still get good results. So this is like the a brand new direction brought by this CLIP. And if we assume that it's multimodal learning, assume that the input data we already have the two, like the modality, then we cannot do this kind of things. This is the first. And also for Koi's question, like it is mainly because that during the pre-training, we are training on like the sentence level instead of like object level. Say that the text is the text part, all of them are captioned, so that when we do the prediction, we also need to design some prompt that looks similar to our pre-training data sets. For example, you can say a photo of, or like which object is in the photo, this kind of the special question that look like a caption to somehow mitigate the trend and inference gap, because it didn't need any fine tuning. Yeah.
I turn off my audio and someone can. Oh,
Use my
computer. Okay, I guess. Okay, this actually happened several times on Tuesday. I was kicked out of Zoom.
I can just mainly use my iPad and then we can use someone else.
Yes, so now.
Yeah, just
That's
Sorry.
So
Okay, maybe I'll just.
It seems all of you mute.
okay, is it working now?
Yeah, now it's fine.
Now it's fine. Okay, yeah, because sorry, Murphy's law. What I worried about is happening, but let's see. I hope this won't. Okay, yeah, because I'm sure. Okay, so you answered the comment. Anyone have, okay, and any other questions?
How does zero shot prediction actually can be done? Because we still need to include that class label in the step 2.
Yeah, so for zero shot, I guess they are just saying they don't need to train on this class labels anymore. They just take these class labels and do the inference. Yeah. Okay. Okay. Let's see.
So far, it has nothing to do with the diffusion model.
So far not. Starting from paper 3, from guided diffusion, we will see 3 papers about diffusion. The first 2 are just things the diffusion model built up, right? Okay. The second one, DALL-E, this was really a big news at that time. So you probably seen this picture many times, like generating this armchair in the shape of an avocado. So the DALL-E paper, I would say, yeah, we can look at the paper title is saying zero shot text to image generation. And then I would say the major question this paper tries to answer is how to combine the text information and the image information together. Because for text information, we already have a transformer GPT, we can encode them. For image information, we also like have a good network architectures, and we can use pre-training method, like a lot of these things. But for DALL-E, it's among the first few works to combine these 2 things together to achieve this powerful text to image generation. And in short, I give you another formula here. DALL-E is just a discrete VAE plus transformer. This should become clear. And the discrete VAE here is more, maybe we call it VQ VAE is more accurate because we will see. Yeah. So the first thing is that with the VQ VAE model, we can do a quick review of this. This is just one slide to give you a general idea. If you want more details, you can follow the link here to go to my older slides from a previous paper reading group in 2020. But yeah, the general idea of VQ VAE is just doing VAE, but with some discrete operation in the middle. So let's say here we have one encoder to get the image representation. Here we have one decoder to reconstruct the image from some given embeddings. If we just replace everything in the middle using Gaussian distribution, then this is just a regular VAE, right? So what people do for VQ VAE is, so by the way, VQ means vector quantization, is that they try to use finitely many discrete embeddings to represent this middle state. So what they call it is a code book. So for example, I just want to use these K embeddings. Each of them is probably, let's say, 64 dimension. So all I want is 64K parameters to represent my hidden space in the middle. I don't want any Gaussian distribution or anything. What this can bring us is that we can represent each input using discrete encoding. So for example, here I have this dog image. I will first get its embedding in this form. Let's say this is just, I think in the study paper, they used the 32 by 32 by D. So I just first convert my image into a 32 by 32 by D tensor. And then for this 32 by 32 by D tensor, I can pick out each D-dimensional vector and compare its similarity to one of these K vectors in my code book. Then after that, I just pick the most similar one and just record its number. So I can represent this 32 by 32 by D tensor as a 32 by 32 matrix with just the code book index in this matrix. Then I only have this like a 1024 dimensional vector to represent my input image. Does this make sense so far?
So is the categorical distribution like like kind of models on labels, or why is it this way?
So in this case, it's like not a probabilistic model. So they didn't assign any distribution for it. They just say that I have this k vectors, and then I will just use a 32 by 32 representation of my input, where each dimension of this 32 by 32 matrix represents corresponds to one of these k vectors. So let's just say so if my original encoding of the image is 32 by 32 by d, I can pick the first d-dimensional vector, right? Like the entry 1, 1. That is a d-dimensional vector, right? For that vector, I can compute a similarity between all these k vectors. Does that make sense?
Yeah, so what is the fundamental reason to use the categorical distribution about?
Oh, you mean the advantage of why
Yeah.
using? Okay, that's because I think there are multiple reasons. One reason is that they feel like using discrete representation, it's like the good way to go, because you can get things more disentangled, and you can just evaluate each of these k embeddings. They probably correspond to some fixed meanings, right? Probably some of them correspond to colors, some of them correspond to shape or anything. The other thing is that you can do more manipulation of this middle, like hidden representation, right? For Gaussian, you can probably add noise to it, do some shifting, but here you can control each entry of this discrete matrix, and to say how well the decoded image change.
But they end up using the Gumbel distribution.
That's not the VQ-VAE. That's actually what this discrete VAE we will see in a moment. So for the VQ-VAE, it's still straightforward nearest neighbor. But when DALI used VQ-VAE, they modify it a little bit. They call it a discrete VAE. Yeah. You are getting a little bit ahead of us already. Yeah.
So the code book are learned, right?
Yeah, it's so this part is a free parameter that
And but k is fixed.
K is a hyperparameter. Yeah, it's fixed.
Okay.
And then so last thing to mention, it's not very important for you to understand today's presentation, but here, because of this discreteness, the optimization of the encoding part, it cannot be easily done using gradient update, because you have a discrete case going on in the middle. So what they do is that they use some approximation, bring the gradient from the decoder part back to the encoder part, so you can use the same gradient to train the encoder. This is on the right is an illustration saying that approximating this gradient, but it's not super important for today's discussion. You can read my slides, or my old slides, follow this link, or read the original paper for more details. So then we can look into what Fred just mentioned, where they use Gumbel softmax. So this is in the DALI paper, they call it discrete variational autoencoder DVAE. But unfortunately, there is another paper called discrete variational autoencoder in iClear 2017 by Jason Raffel. So these are two like very different ideas, right? So if you go back home and search discrete variational autoencoder, don't get confused, because the DVAE used in the DALI paper is like a very simple modification of VQ-VAE, what we just saw in the previous paper. So what they are doing is that now in each of this entry, right, in the VQ-VAE, we just store one index, like 1 to k, just pick a number and store it there. But in this DVAE version, they store a distribution. So let's say in this case, maybe make a little bit bigger. In this figure, they choose k to be 8,192. So from 0 to 9181. So each of this entry will store a distribution telling you store a distribution of this 8192, size 8192, and tell you how much portion they want from each embedding in the code book. And then Because this is now a continuous distribution, they don't need any, say, nearest neighbor or any vector quantization to in the middle. So everything can become like a continuous. Then in order to get a more discrete flavor, they use Gumbel softmax in the middle. So when you sample from this distribution, you can still get something close to the discrete version. So yeah, I guess this is a good modification because we don't need to do this kind of copy gradient update, right? But using the Gumbel softmax in the middle, we can still enjoy the good properties of discreteness. But yeah, that's basically it. The DVAE is not too much different from the VQVAE. So if my explanation was not super clear from the previous page, we can look at this example here. Assuming the code book is just only has 4 code or 4 embeddings in it, right? So the encoding part will be giving you this avocado chair, and then what you do is that you just encode it, and you generate this 4-dimensional embeddings, and then for each of these 4-dimensional embedding, it tells you, okay, this is a distribution. You should multiply these 4 numbers with this 4 code in the code book, and then get your representation of the image. Then during decoding, you just do exactly that, but with the Gumbel softmax sampling here, right? You don't want this more uniform distribution, but you want one of them to stick out, let's say 0.95, but still you do this multiplication, or you can think of it as weighted average, whichever you like, but you just multiply these 2 together, and then you get the vector that's ready to be plugged into the decoder. Okay, is the DVAE clear here?
This idea is very similar to Team's idea. So
Of
Teams,
wage paper.
it's a ICML on the
Okay.
also proposes 3D code, but the purpose is
Yeah, I think he mentioned the VQVAE in the related work of that paper, if I remember correctly. Yeah, because the VQVAE came early in 2017, or maybe even earlier, late 2016. But this DVAE used in the Dalle paper, it's 2021. Yeah. Okay. Let's see. So I just told you a formula about this Dalle, which is discrete VAE plus transformer. So we already have the discrete VAE ready. Let's see the transformer part. So in this image, over here is just VQVAE. So Dalle is like you can think of it as like a 2-step process. You can just train the VQVAE first without worrying about anything else, and you don't use any text information at the moment. Just train it using these images. Then you have this transformer, which is like Yizhou just mentioned. This can be a multimodal transformer because you will input both text token and image token into it. So what they are doing is something like this. Let me draw it here. So you have this image. First of all, this will be your input, the text, and this will also be your input, the image of the avocado chair, right? So you get a pair of this, a text caption and the actual image, and you already have your DVAE trained. So what you can do is that you get this image embedding from your DVAE, right? Because you have it trained. Then you encode your text to get this text embeddings. And then you put like a start of a sentence, token here, right? And then you use the transformer to do auto-regressive prediction, right? You use the text encoding plus the start of a sentence token to predict the first token of your image encoding. Then once you predict it, you bring it here, you put it here, and you use the text plus start plus the first token to predict the second token. You do all of this until you predict all of the tokens in your image. That's how you train your transformer. Later on, when you want to use this to do text to image generation, what you do is that you just take the prompt and put the start token here and just keep predicting the next token for the image until you get all the image tokens. Then for this predicted image, it's ready to go to the decoder to generate the actual image. That's what's going on for the second module of DALL-E here. Just this transformer that can take both the text caption embedding and the image embedding.
For that preferred kind of embedding already
For which embedding is it?
for the
Purple one? Yeah, it's already. So the purple one actually corresponds to this. Yeah. So it's the continuous one. Yeah. Okay. So this is the major idea of DALL-E. We will see, because DALL-E 2 is the latest. We will wait for 2 more papers to see DALL-E 2, which also does this 2-step training. It's just the one step is replaced by clip, the other step is replaced by diffusion model.
Did they mention why this one works so well?
So actually, this is a hard question, and I think even for the paper itself, if you go ahead and read the paper, find a lot of details going on. They talk about the architecture, why they use 64 attention has, and etc. Right? They did a lot of those tricks. It's hard to say which trick helped the most, but you can see bring these things together, they can do this amazing text to image generation. So for some of the important ones, they provide some hypothesis and explanation, but I would say those are at the high level. So I include some of those analyses for the DALL-E 2 paper and the GLADE paper, but not for the first 2 papers, because we want to look at the latest. Yeah.
Oh yeah. Before moving on, maybe I can leave a very quick comment of this DALL-E 1. So the high level idea, because like Shichang just mentioned the methodology they use, but didn't mention too much of why they're utilizing that. I think the most initial motivation of building such architecture is that vanilla text decoding is to generate the discrete token. For example, the GPT-3 already got very good high quality like text generation. But when we do the image generation, mostly we are still doing it in a continuous space. So I think the initial motivation of that paper and also many of the following up works is that whether we can somehow represent the image representation into, for example, a sentence or like a list of like discrete tokens. But initially we don't have that kind of the supervision. So they in this paper they somehow utilizing this VQVAE to somehow build such code base. So if we can imagine this code base might be another language, maybe a language that introduced by this model itself. But if we introduce it as like a human language, for example, in Chinese or English, then maybe you can regard this like generated like a discrete codebook as just a vocabulary. And this kind of transformer, what it did is just to turn the capture into these image tokens. Yeah, I think this is the key, like initial motivation of this work.
Yeah. I think it's a pretty good comment, because if you go ahead and check the paper, although here we call it a code book, so in some of the papers they actually just call this code book a vocabulary. They call it like an image token vocabulary. Yeah.
I think that's a very good initiative. But the following that, I still have the question, because image is different from text. So we don't really have that difference.
Right.
So when we try to predict the next vocabulary in the image, because that means what's the meaning of the order?
The meaning of the order. I guess maybe because the image is square or like at least a rectangle, they just specify the order, like maybe chop it into small pieces, and then maybe from upper left to bottom right using that order.
So we want to predict the next pattern.
Right. So let's say, so in this case,
Let me rephrase this first.
okay.
So for the image, they're going to be 100% wrong.
Mhm.
Is that?
That matters. So if we look at this one here, so even this image, they actually turn it into a 32 by 32 by D, this tensor. Yeah, so this 32 by 32, the order matters here. Yeah, so it's just like, yeah, they label it, say 101 or 31 until 1023. Yeah. So I guess if we first chop all image into like a same size, and later on we always follow the same order of this from, say, upper left, bottom right, then we can assume we have an order for the image tokens. Let's see. So you said another paper?
Yeah. So another thing I want to mention is that this kind of like discretization idea, after the study E, also have many follow-up work, and one of the pioneers is like one of the most recent image generation work. And in all this work, also in many recent days, they just call this VQVAE as a tokenizer, very similar to when we turn like the sentence, like each word into an ID, and the basic idea is just to turn the image into a list of like discrete ID tokens. And Andrew mentions a very good intuition that the order matters. So in some of the recent works, they keep the order of this kind of generated discrete tokens, and they somehow utilizing the autoregressive model to generate that. So you can imagine like when we draw an image, we will firstly like draw the background, and then put the, for example, the most important person, and then draw his details or something like that. So in that case, each of the added tokens will have a specific meanings, without like just like we can just like randomly shuffle them.
Okay, calling it a tokenizer is something I didn't know, but that's very interesting. Yeah.
But, I was saying that the order does not necessarily correspond to the spatial order. They could be a different order. It might be first and some.
Yeah, because in the paper I show, they train this tokenizer by image generation, so that this list of like tokens will be matched to like maybe the initial few tokens are more like relevant to the background, something like that. But it didn't specify the true meaning of them, but just try to learn end to end. But yeah, if we have like some more ground truth supervision, maybe we can get more richer understanding of the tokens. Yeah.
Okay, so in practice, we'll still utilize spatial order to observe order.
Yes.
There are two different kinds of right?
Mm-hmm.
Yeah, I was more like semantic order.
Mm. I guess at least here it's following the spatial order. So that's the data. So there's one question from Vivian in the chat. Does it require the test data set have the same size? So in our case, actually for this kind of text to image generation, we don't have like a test image, right? Because we just generate the image using our decoder. And then when you train the decoder, you already specify the size, like what is the image size the decoder should output. Yeah. So you are not using like a later on for the later papers, they sometimes do conditional generation, like they encode one image and takes that image embedding into the generation process, so you can generate something similar to the image you condition on. But at this point, where once the model is trained, we are not taking any images to test it. We just generate new images from it.
I see. The reason I asked this question is because as you just from my understanding, so essentially it will just generate a sequence of pixel, and then after all, you will trying to, for example, transform this sequence of pixel into a image, and then because during the training stage, the potential position of each pixel might be learned while we're trying to training this model. And then if like the generated image have different size, of course, like this potential position information should be different. That is the reason why I ask whether there's like some very strict requirement between the training set and the testing set. Here, what I'm trying to say for the training set and testing set is like, if we train to generate if we train on the image with size, for example, 32 by 32, then we can only generate image of the size 32 by 32.
Right. So
I see.
I'm skipping ahead to a later slide. So you can see in later work, people actually use this, what they call cascade generation. And then they will first generate something maybe a smaller size. And then they use other modules to do super resolution. So they can get images of larger size. Yeah.
I see. I
think
see.
if we go back to what we talked about so far, I don't know, the paper doesn't explicitly mention, at least I don't remember it mentioned the problem you asked. Probably they assumed that they will just generate image of the same size. Yeah.
I see, because from my understanding in this framework, there's no, for example, position encoding. Therefore, if we're trying to handling different size, that might be a problem. That is just my curious about that. Yeah.
Right. So I guess for later papers, that super resolution idea became like a standard step to do.
I see. I see. Thank you. Thank you for the explanation.
Yeah. Any other questions? Okay. Yeah. Great to have all of this discussion to help all of us here to learn more. Let's move on actually to the diffusion part. Okay, now we can connect to what we talked about in the first 2 weeks, the diffusion model. The first thing, paper I want to talk about is this called guided diffusion. This paper used the title saying that diffusion model beats GANs on image synthesis. And then they show these examples where, for example, this one is generated using the big GAN deep, the state-of-the-art GAN model at the time. And then they also show some examples generated by their diffusion model with guidance in the middle and the ground truth pictures. They measure it using the FID score, which is Freshy interception distance. Yeah, I can explain more about it, but I guess maybe we can save some time to discuss the other papers. But ask me if you are curious about this. It's equivalent to the Weatherstand-2 distance. I actually spent quite a bit of time reading about this score. But just to tell you, the score is like the smaller the better. So in this case, the GAN generated image is not as good as their guided diffusion generated image in terms of the FID score.
Here, the distance defined
over two distributions. And then originally the mathematical object is just called the Freshy distance, but they also use an inception model. So meaning you have a two set of images, you encode both of them using this inception model, then you get two set of embeddings. Then you can look at these two set of embeddings as if they are distributions, then measure them using the Freshy distance. Yeah, that's the idea. So it's actually a little bit strange to me when I first saw this, because the evaluation depends on a given inception model, which is just a large neural network. So it seems like when people evaluate one neural network, they need to do evaluation built on top of another neural network. So yeah.
So I read something about how to maximize the mutual information between two distributions.
Mhm,
And it can be transferred into the kind of optimization problem,
mhm.
which can be viewed on some, so here they are all related.
Wait, so,
Mutual information is very hard. to-
okay, yeah, that I
So
know.
in our case, they turn the problem into some
Optimization, okay, and then
which can be built upon on a level.
can be built upon, okay.
I'm not sure what is related, but it sounds related.
For this part, I'm not sure, because they only use this score for evaluation. For the point you mentioned, it seems like the last part also involves some learning, right?
The objective could be just to maximize mutual information between.
Yeah, okay, okay, yeah, still, I'm not sure, because in this case, like this inception model is some pre-trained neural network, just to use them to convert the image into embedding. Then they can evaluate these two set of embeddings as if they are distributions. Then, yeah, so, okay, I see, I
Just
see.
have one question. What is the gamma here? The big one.
Gamma.
The
Oh,
one-
right. So this one, this represents the space of all possible distributions. Like these are two measures, mu and nu, and this is like a space over this coupled distributions, and this is like all measures on top of this with the marginal distribution matching mu and matching mu. Does that make sense? So think of it like two-dimensional. Think of all distributions that are on top of two-dimensional vectors. You know their projection on X and you know their projection on Y. So this is just saying I pick all possible two-dimensional distributions with fixed X projection and Y projection. Yeah, that's why this is equivalent to Westerstand 2 distance. Right. Yeah. So usually when people put these two things together, they call it coupling. Like you already have two distributions, you just put them as like say to concatenate them together, then they call it coupling. But compared to general distributions of let's say all possible two-dimensional distributions, you still get only a subset, right? Because you fix the X, Y projection. Yeah. Okay, this is something I'm really interested in discussing, but I'm not sure for everyone else because it's a bit digression. So we can definitely talk about this offline. Yeah, because it's just an evaluation here. Because otherwise, I feel like this 6.95, 5.59 probably doesn't make too much sense. But okay. Let's look at this. This is what we talk about in the first 2 weeks, the DDPM model, denoising diffusion probabilistic model. So we are all very familiar with it right now, right? You have some data, you have some noise. The forward progress is adding noise and transfer the data into pure noise. The backward is sample from this noise and gradually build up your data, right? These two algorithms also, Zhenyu showed them last time. So basically, what we are doing is that I just have a neural network to predict the error I generated at each step, right? This epsilon depends on theta, takes into this is the original data and the error and the time step t. You can estimate the error and minimize its distance to the actual error, right? So a thing I want to point out here is this red sentence here. So during the reverse process, we can either choose to approximate the mean of the normal or to choose to approximate the error of the normal. These two are like equivalent. But if you go ahead and read the papers, you will see that the OpenAI papers, they all choose to approximate the mean. And the Google Brain papers, they all choose to approximate the epsilon. So you will see both settings. But and I will mix it a little bit because I have formulas from like both series of papers. But just keeping in mind that either you approximate the mean or you approximate the error is equivalent. You just have your neural network to output your approximation, and you probably do some reparameterization to turn it into a mean or turn it into an error. And then the algorithm 2 corresponds to the sampling stage. If you want to generate a new image from the noise, what you can do is that you can just start from here and generate the noise using your neural network and generate more and add it on top of the existing noise. So if we look at what's going on here, this DDPM model, it's what's called unguided in this paper I'm talking about, and the paper is trying to propose a guided version of it. So the difference is showing on this slide. So first of all, if we take the algorithm 2 for the sampling stage, we can simplify it a little bit, or let's say we can rewrite it a little bit as this, right? So in the original algorithm 2, you will generate this normal variable and use your neural network to construct a new area for the next stage image. And then if we rewrite it a little bit, you can think of it as using your neural network to generate a new mean, and then just a sample from the normal with this mean. The first, okay, and then for the DDPM model, they actually fixed the variance. So this small sigma t is something you are giving. You never tuned it. It's just a parameter. So when you sample from the model, this model has a fixed variance and some mu you just generated from your network. And then what this guided diffusion paper do is just change this thing, change what's in this red box. First of all, it makes a learnable variance as well, right? So other than the neural network for approximating the mean, you have another neural network to approximate the variance. So you have two things you can learn. The second thing is that we can add this what they call classifier guidance to the mean. So I will explain what's classifier guidance in more detail on next page, but just looking at the distribution, what this guided diffusion do is just making the variance learnable and shift the mean by this expression, right? Just compared to DDPM, the diffusion part is not too big. The difference is not too big. Just shift the mean and makes the variance learnable. So yeah, for that shift, we will look at it here. So I just copy paste it here, and we can look into what this shift means and why do we need it, right? So we are actually doing this kind of shifting because the original diffusion model just generate some image from noise, right? Now imagine we want to do conditional generation, like I want to generate an image not from a noise, but from some label. Let's say I want to generate a dog's image. Then because I already know this image should be labeled dog, then I can take this information to generate the image that contains a dog. But how to incorporate this label information into my generation? This is what they call a classifier guidance. What they do is that, okay, they can train a classifier. Let's say train this classifier on ImageNet or anything. And then they represent this classifier using this P phi. So what this classifier do is that you can give it any image, it can predict the class of that image. Then during your diffusion process, right, each xt will be, like, let's go back here. Each of this will be one xt, right? It will be some embedding has the same dimension as your image. You can actually think of it as like an image, just with some noise in the image. So what you can do is that you can plug that noise version image into your classifier and actually get this log probability. Then you can take this gradient with respect to your input image. The meaning of this is saying that in which direction I should move in order for my image to maximize the probability of this label one. Does that make sense so far? So you have a trained classifier, can already pretty accurately predict the image class. Now you have an image, but this image is full of noise. Then you plug this image into the model, takes the gradient, then you will get this score telling you which direction you should move to turn the image to maximize this Y, right? And then what they do is that they just take this score, like scale it by the variance, and as is like a pre-specified parameter they can tune, and add this whole thing to the mean. So we can actually also draw it a little bit here. So let's say originally you have the mean here, and then it's probably a normal. Let's say this is just the first standard deviation. When you draw from this normal, you probably pick some points here, some points here, right? When you do the sampling. Imagine this is a high dimensional space. This is a space has the same dimension as your image. So the diffusion model will give you all these blue points, right? But what they are doing right now is that they shift it a little bit, maybe here, right? So they shift it a little bit. This is V plus S times this sigma times this gradient. I will just use the gradient because the expression is so long. But what they are saying is that as long as you move towards this green direction, you will maximize the probability of image being this green class, whatever it is, like a dog, right? Then later on, when you do the sampling, if your mean has moved, then you will get these green points, right? Which are more likely to be a dog. Okay, and then we can talk about this S a little bit. Two ways to understand that. So one way is, okay, I need to go back to here. One way is that probably originally your score, oh, sorry.
What's interesting to me is that they decided to learn the variance in the first step rather than after the shift. Because you see, like, they learn the variance, right? So, but they didn't decide to do the learning of the variance after the shift or before shift. Because I'm thinking if you learn the variance after, then you have to kind of potentially incorporate more information.
So here, okay, so here there are several things going on. So for learning part, for both the mu and the sigma, the learning is done at this stage. They are just doing sampling. So you can imagine the thetas are fixed. So they add this classifier guidance only when they do the sampling. Yeah. So at this stage, the variance is just generated out of the neural network, right? Yeah. And then I think what you are saying is that when you do this normal shifting, you can consider both variance and mean information, right? Yeah. I agree that could make it like more informative probably because they are just simply multiplying it here. But maybe we can do something like more complicated here. Just get back to this S parameter. So there are two ways to understand that. Let's say originally your gradient is this big. If you multiply it by a bigger S larger than 1, you will move more towards this direction, right? Means you are closer to the point that will maximize the Y. The other way of understanding that is that because you have a gradient, this expression is actually equivalent to this expression. So you can stare at it a little bit. Z is a constant, take the gradient, it will be gone, and this S will come down from the log to here. So what does this mean, right? If we agree these two are equivalent, what's on the right is actually your original classification, but to some S power. If S is like a number larger than 1, this will turn, say, something from this into something to this, right? So basically it will make the classified class stick out. So you get a peaked distribution. Then you renormalize it using this constant. So that is saying the second way of understanding this S parameter is how much you want your classifier to your predict class to stand out, right? So both ways, in terms of how much you move or in terms of how much this distribution should be peaked, you can understand how influential this classifier guidance can be. And in reality, people found that using a larger S, usually 3 or 5, like something larger than 1, can give you better results. Oh, in this case, they even use the 10. So they try to generate a dog class. If they just use like classifier guidance with 1, it gives the image on the left. But if they use classifier s equals 10, it gives image on the right. You can see there are some cases it's not really a dog, right? But here you get more dogs.
Is FID like a standard thing for comparing between different?
At
diffusion
least in the papers I have read, like paper we cover today, FID is the standard metric.
okay.
There are other things like inception score IS and a modified version of FID called SFID. These are all like widely used. So I think it's like IS first. Later on, people figure out FID is better. Later on, people say SFID is slightly better. Yeah.
Okay.
Oh, it's that thing I mentioned on this page. This fresh inception distance.
Because like the guide they give for the diffusion process itself looks quite similar to the FID score they're measuring. The latent space embedded like probability distributions mean difference is just like what they're basically doing for the guidance. I think FID is like quite embedded itself into the equation itself for the guidance. Yeah.
I think so in the first paper proposed this FID idea, they actually used they did more formal mathematical derivation saying why this is good, why it's reasonable. Later on, people just take it as a standard metric. Yeah.
I just want the other comment. I think this guidance idea is very interesting. There's another paper that I recently read that was related to the paper reading group on Tuesday on molecular generation. Basically, they have guidance to direct your diffusion process to optimize certain molecular properties, such as I think the Professor Wang mentioned the energy function. There's like a written paper.
Okay. Yeah. Yeah. Maybe you can share that paper
Yeah.
with us after the reading group, and we will see more guidance in the last 2 papers. So here we have classifier guidance. There are classifier free guidance and clip guidance. We will see them, right? Okay. So for this glide paper, again, I summarize it using this formula here. It's just a diffusion model plus classifier free guidance, which is a new guidance we will talk about in a minute. But the major question it tries to answer is just like the Dalle paper, because it tries to do text to image generation, or it's actually a little bit more. They also do image editing. But the question they answer is, again, how to combine the text information and the image information together. So here I'm showing some things the glide paper can do. They can generate something like this. You give it a caption, a hedgehog using a calculator, it will give you this image. Or you can say that a man with a red hair, then you just mask out this part, ask the model to do editing. The model will like put red hair on this man's head. So let's see how this model achieved it. So basically, it's again conditional generation, more specifically conditional diffusion model generation. Just try to think of a way to use this text information when you do either image generation or editing, right? So let's compare this. The first version, the regular version, is just the DDPM, but we also turned the variance to be learnable. This is the most basic version. On top of that, we can have classifier guidance. This is what I just introduced in last paper. You can add this S times the variance times the score, right, to shift the mean. Then when you sample from the normal, you get something more aligned with your classifier. So what this glide paper explored are 2 more things. One is called clip guidance. Basically, it's the same idea. You're adding a term to shift the normal mean, but how this term is computed is different. So instead of training a separate classifier to classify the class, you take the clip model. Remember, I should have it. Okay. Let's see. Remember, what the clip model gives you is this 2 encoders, one for the text, one for the image, right? you can just take a pre-trained clip model for granted and use these two encoders. So in the GLIDE paper, they just take the pre-trained clip model and then they take the image encoder, name it as F. They take the caption encoder, name it as G. And whenever you want to condition the image XT on some caption, you just get this image embedding and text embedding by plug them into the clip model. And then you can take their dot product, right? This will give you score. You can sort of think of it as classifying using the clip model, but they just refer it as clip guidance. Similarly, you can ask, how should I move my XT such that this score will be maximized? Then you can use this to shift your mean. Finally, there is something they call classifier-free guidance. So sorry, here I'm switching notation a little bit from mean to error, but just like I told you, this is actually the same thing. Just because these three are from OpenAI, these two are from Google Brain, they follow the different notations. But shifting the mean and shifting the error will be equivalent up to some like reparameterization. In this case, what is the classifier-free guidance is saying that I don't need any clip, I don't need any classifier guidance. It's just before when you decode when you try to sample from your image, let's say from here, right? I just take this noise and get another image of the same dimension. But right now, if I want to use the classifier-free guidance, what I do is that I will always have a placeholder here. Whenever I have this image, I try to bring it to the previous step. I will also concatenate a text embedding here, right? And then this text embedding probably says something like cat, right? You just encode this cat using a language model and get its embedding and concatenate it at the end of this image. Then once I get here, I just put the same embedding again, concatenate it at the end of this noisy image and bring it forward again. Until the second last step, I have this cat embedding here and bring it to the final generated cat. In this case, because each step, I have this caption information attached at the end, my generating image will know, okay, this image should incorporate the cat information. This is the whole idea of classifier-free guidance. And then whenever you have a label Y or a caption C you want to condition on, you just take its difference versus plug in like the empty, like a padded empty vector. Then you just move towards that way to shift your error or equivalently shift your mean for the other cases. Yeah.
How would you compare like clip guidance versus classifier-free guidance?
Okay, that's like a major point of this paper. So they didn't compare it like theoretically. They did some experiments to compare it empirically, and they find in their case the classifier-free guidance outperforms clip guidance. There are some discussions in the paper. I didn't include them here, but you can go ahead and read about it, saying that clip guidance is more vulnerable to adversarial attack, and then using that guidance can probably lead to some adversarial cases which are less realistic. But I would say that's more like a pure argument without too much distance. So just a hypothesis, yeah. And then just speaking of which guidance is better, the classifier-free guidance paper, which is another paper from Google Brain, when they proposed this idea, they mentioned that, oh, it is better because you don't need to train a separate classification model or clip model, right? You can always rely on your original model. Just put an empty set there or whatever you want to condition on there. Also, in this case, you are not restricted by using a label, using caption, or using anything. You can just, as long as you have a model can encode it, you can condition on everything. Not like the classifier case, you need to have a label, or the clip case, you need to have a caption. Yeah, it's more flexible. Idro, your question?
No, so my question was hard. Yes, I try to understand for the coherence matrix generation.
Okay.
Because it could be very huge from 2 by 2, but in practice, do they make it like more spots?
Okay. Yeah, this is a good question. I actually,
Normally should be diagonal.
yeah,
Standard practice.
they maybe do something similar, like simple, like generate a vector and make
Yeah.
it a diagonal. But this is just my hypothesis, because otherwise you have to make sure it's symmetric. It's
Yeah, it's really hard.
okay. Yeah, generate a covariance matrix itself can be a hard question.
Yeah.
Okay, I don't know how they did it in the paper, but this is a very interesting point.
Yeah.
Yeah.
That's the question. Say you have like a classifier that works well, and you have like fixed class labels. In that case, would you still use like classifier guidance, or would you use like the classifier guidance?
They didn't compare classifier guidance versus classifier free guidance in this paper. They compared the CLEEP guidance versus classifier free. So if you think of CLEEP as a well-trained classifier, what they say is classifier free guidance wins. Yeah. Yeah, I guess a lot of these things are more on the empirical side, because if it's classifier guidance, it definitely depends on how good the classifier is. Yeah. Okay. Yeah, for the covariance generation, I will go back and check it. Yeah. That's a very interesting point. Okay. Also, how can this kind of model do the image inpainting is that during the reverse sampling process, right? So you will get an image, and whenever you generate, say you go from xt to xt-1 to xt-2, whenever you sample one more step, you replace the noise with what you already know. What do I mean by that? Like in this case, you just keep this masked here, always generated. Once you get a new picture for all other places, you replace it with the background with the man's face and the sofa. And finally, you make sure other parts don't change, only the hair changes. So with this kind of interrupting, they can do image editing. Say, for example, put a waist on top of this table. Yeah. This paper also mentions some limitations, like the glide model cannot generate something that's unusual, right? For example, if we're asking an image about a mouse hunting a lion, then it doesn't make too much sense, because it's also hard to imagine how a mouse could, how to represent hunting in this sense, right? Also, you may ask things like a car with triangular wheels. You can see in some of the generations, it captures the idea of triangle, but I would definitely call this are the cars with triangular wheels. But this could be some limitations, I guess, later on follow-up works will try to overcome.
Yeah, so I just have a quick question. So with this kind of generative models, right, especially when you are considering this unusual scenarios, I think mostly the problem would be like your distribution is a unimodal distribution that you have the multiple issue, or like your variance is still centered around the mean so that it doesn't have the coverage, full coverage of the sample space or something like that. And for diffusion models, you always have a normal, right? You know, always have a normal distribution. So the assumption is like a unimodal distribution. So unlike the normalizing flow, which you end up with a multimodal distribution. So would that be something that's related to this limitation, do you think?
I guess that could be. Also, I guess some related observation later on was that people find out if you train your diffusion model with the specified domain, say paintings only, or like so whatever, like if you reduce your modality of your data distribution in the first place, then the diffusion model can do much better generation. In this case, if you wanted to include, say, all possible images in the world, then it's hard to capture these unusual cases, right? Yeah. Okay. We have until 3:30. Okay. Yeah, it's good to have all of these questions. Let me try to finish the DALL-E 2. I guess I don't have a time to do the disco diffusion live demo, but I can show you some examples I pre-generated. Okay, the DALL-E 2, we could finish it in 5 minutes because it's actually simple. In the paper, if you go ahead and read the paper, in the paper they call it unclip. You can see how related it is to clip. It's just later on in the social media or when they do advertising, they call it DALL-E 2. So these two are actually the same thing. These pictures you probably have seen before. Panda mad scientist and this Kogi's head as a nebula. I saw them on social media multiple times. But this is what DALL-E 2 generated. I can also summarize a little bit. It's just a diffusion model plus embeddings. At this point, we should be very familiar of both of these, so we can easily get what DALL-E 2 is doing. This is just showing DALL-E 2 has good performance. Let's just skip it. Okay. For DALL-E 2, it's like DALL-E 1. This is like a two-step process. So they are doing two things. In DALL-E 1, it's like a VQVE, just to train it. After that, you combine transformer with it. In DALL-E 2, it's like clip, just to train it. After that, combine the clip with what they have here. They call a prior and a decoder, right? So everything above this dashed line is just a regular clip, nothing fancy. Train the clip, get the text encoder, get the image encoder, and then that's done. So what's interesting, what's new is happening down here with this prior model and this decoder model. Let's see what's happening. Okay, clip, just to remind you what it's doing. Then for the decoder, it's a conditional diffusion model, right? With these two diffusion upsamplers. Let me remind you again what the decoder is. The decoder is something that can give you an actual image. What it takes in is an image embedding. In this case, the blue ones will be the text embedding, and these brown ones will be the image embedding. When you train the decoder, it will just be a conditional generation model takes in this image embedding, right? If we just have like an unconditioned diffusion model, you can just generate this kind of image out of noise, right? But we just introduced the conditioned diffusion model where you can condition on label or condition on caption. In this case, they are just a condition on this image token, meaning if you have some image embedding, you can just concatenate it at the end of your noise vector. Every step when you try to sample new noise, then you just can incorporate this image embedding information to do conditional generation. That's basically it. Not too deep, but and after that, once you get that small resolution image, you have two super resolution modules to make it to make a larger image. I guess I don't want to spend too much time talking about it, but you can read this paper, the cascade diffusion model here, and then it tells you how to use the UNet to achieve these two super resolution generation. That gives us the decoder part. Then is this part of what they call a prior. Remember, the decoder part takes takes the image embedding and generate an image. But this image embedding is it's just some vector. It's just conceptually we think of it as an image embedding. So in reality, we don't have this image embedding. What we want is text to image generation. So we will start with a sentence like that and try to get an image like that. So somehow we need to go through some steps here, end up with the image embedding and condition on this image embedding to get the generated image. So how do we get from this giving a corgi playing a flame throwing trumpet to this brown image embedding is what they call a prior model, right? Is this clear? So the simplest way is that you can just take any language model you like, just say GPT, transformer, whatever, just encode this caption, get an embedding of the same dimension, and then pretend that is the image embedding, right? The authors did that, but the performance was bad. What they did was that they used the clip encoder to encode this text embedding. So up here, they call it a clip embedding. It is the embedding of the text, but because it's encoded using the clip pre-trained text encoder, they call it a clip embedding. And then they use a diffusion model here in the middle to turn this clip embedding into another clip image embedding, right? These are just the two vectors of the same size, but you have the diffusion model in between to conceptually turn it from a representation of the text to a representation of the image. Then you plug it into your decoder to get the image. These two boxes. Actually, I'm not sure. Yeah, I know the prior model is just a diffusion model. Yeah, probably represents sampling the noise step by step, and then. So I feel like this is probably like saying this is noise, this is what you want finally, and you generate it step by step. And each step you will generate a new thing like this and add it on top. Yeah, for that part, I'm actually not sure what these boxes mean.
So the box are like they utilizing two model. One is autoregressive model, the other is like a diffusion model. So the first is diffusion, the second is autoregressive.
But they never use those two models together. They are just saying you can have two different choices. You can choose autoregressive or diffusion. Oh,
Yeah.
Oh, I see. Yeah. So in the paper, they are saying like for this prior part, you can either use diffusion model or use autoregressive. Then this one is the autoregressive one, I guess. Okay. Then it's a little bit confusing because the two models are not used together. It's just you plug in one or another in this case, because you only need something to turn this d-dimensional embedding to another d-dimensional embedding. It's just conceptually represents text and image. Yeah. Yeah. Okay. Yeah, here is some like a ablation study they did. They were doing something like, okay, why don't I forget about the clip? I just encode this text using a GPT or any language model and just plug it into the decoder. And the result was that, okay, it's not good. So if I just use the caption encoded by a language model, it will miss the calculator. It's the same prompt, hashdog using a calculator. The caption only will miss the calculator. And then if we use the caption class, the clip text embedding, meaning I just get this blue one, but no autoregression or no diffusion in the middle, I can get something like this. But if I use the caption plus this clip text embedding turned into the brown one, I can get this final image with hedgehog in the middle and a calculator. So just to illustrate that all the modules they propose are needed to get good performance. They also did something other ablation study. For example, this one is for testing the decoder. Because we talk about that for decoder, we can condition on any image embedding we like, right? So what they try to do is that they can condition on like two different image embeddings and then try to interpolate, try to generate something in the middle. And then if we condition on this one, we can, this Van Gogh's painting, you can generate something Van Gogh style. If you condition on these two dogs, you can generate other dogs, but in the middle, you have the interpolated image. And what's more interesting is that you can do interpolation for the text to achieve this result. This is like saying you have two captions. One says a photo of an adult line. The other says a photo of a lion cub. But just to get the text embedding of this, get some intermediate steps of these two text embeddings and condition on those intermediate text embeddings to generate this a series of images. You can see you can generate this interpolation style, right? I guess this is much more interesting because for interpolation, people have done a lot of it for images, but in this case, you can actually condition on interpolated text to achieve similar results.
There's a question.
Oh, there's a question. Oh, you mean, yeah. So the question is asking, the previous paper is Glide. This paper is DALL-E. Why this is better than Glide? So actually the paper is not claiming it's better than Glide. So it's claiming it's better than Glide in some perspectives. There is one So because basically the two papers are by the same group of authors. And then this is one thing comparing, they use the different metrics, say the photorealism and the caption similarity and the diversity, use different metrics to compare the DALL-E 2 and the glide. What they found was that DALL-E 2 will usually win in terms of diversity, but for the other two, the models are comparable to each other. So in other words, they can both generate realistic images, but DALL-E 2 can give you more diverse images. And DALL-E 2 also has some like limitations. For example, they ask DALL-E 2 to generate a red cube on top of a blue cube. And you can see that the model can sometimes misunderstand which is on the top, right? They probably put the blue on top. And then they ask DALL-E 2 to generate some images with text in it, saying a sign that says deep learning, then it's hard to put this text on the image. So these are the actually hard cases, like the unrealistic scenarios. I think like both models haven't overcome these kind of hard cases. So we will see whether future works can explain why this is happening and solve these limitations. You left one or right one? Both. For the left one, I think it's hard because so here you are telling the model a bunch of things, right? You have a red and blue for it, and you have top and the bottom for it. The model needs to figure out which one matches with which. So it can capture the information red and blue, but maybe when the model encode this caption, the red and the top didn't match that good. So they sometimes they will put the blue on the top. Right. Yeah. So actually, I'm not putting another example here, but in the paper, there's an example of this kind of generation, where they ask to generate image of a corgi wearing a color 1 bow tie and a color 2 patty hat. What they find is that the model sometimes mix these two, mess up with these two colors. So even though you tell it should be a red bow tie and purple hat, sometimes the bow tie is purple and the hat is red. They say both pictures. So what they hypothesized was that matching the object and the adjective in the caption can be hard. This is one thing. The second thing is that about having that deep learning sign, right? It's like to understand this deep learning conceptually versus treat it as some text you should actually show in the image. Maybe the model cannot distinguish these two very well, right? So it probably puts something deep here or anything, but it cannot accurately express the deep learning, the whole phrase here. Okay. Yeah, we are a little bit over time. I'm sorry, but lastly, I just summarized the formulas I give you in each of these papers, CLIPE, DALL-E, guided diffusion, also glide, and DALL-E 2. So for all of this, you can see it's not something super novel or super hard. Just take the existing modules and do this plug and play. And with very carefully designed architecture and hyperparameter tuning plus huge computational resources, they can achieve good results. You can check this as a cheat sheet if you later on want to get back to these models. So finally, let me quickly mention the disco diffusion. This is like an online demo for you to actually generate text, generate image from text. I didn't choose DALL-E 2 because you need to apply for access to DALL-E 2. But for this disco diffusion, is free. You can follow this link here, or simply Google search disco diffusion. The first result will be this link, and you can play with it. If you want to recommend it to other friends, you can use this link here. This is like a 40 minutes YouTube video with no background requirement for beginners. So because the notebook is so well designed, you can ignore all the code part. They just ask you this, fill in the blanks. You can just fill in the numbers. And you actually, for most of it, you just use the default setting. That's good enough. As long as your friend knows what is a Google Drive, then you can send this link to them and ask them to play with it, right? No need to be a computer scientist or engineer or anything. Finally, I can show you some results I generated. This one on the left is what I picked online, generated using this prompt, basically asking for a lighthouse. What I generated is on the right, because I don't have too many computing resources, so I generated a smaller size of image. I would say there are multiple factors that's important for generating good image. The first of all, the most important one is definitely the model itself, right? We already talked about if it is domain specific, then the result should be better. If it's too general to incorporate all possible images, then it will be hard. Also, the prompt is definitely very important. What you tell the model to do, what it can condition on is important. And then the image size is important. For example, in this case, the image is like a rectangle. You can see there are several lighthouses in it. But because I picked a square image, we can see only one major lighthouse, probably a small one here. But I would say image size definitely influenced the result. And also for the resolution, you want to increase your diffusion steps to get higher resolution images. Lastly, this is another prompt I designed myself. I didn't I didn't pick those good prompts people already verified online. I just asked Disco Diffusion to generate a portrait of the smartest mathematician. You can see what I got. This is, the good thing of the Disco Diffusion is that you can save all these middle steps. It started with something like this and ended up with something like this. You can see it gradually adds this, say, beard and glasses, and then gets more details at the end. It tried to add the sigma and x-axis and y-axis of the image. Well, it's not so realistic a person could look like this, right? But you can see how this prompt can influence the image generation. Actually, this is not the only thing, because for the generation, usually it will generate a bunch of examples for you with the same prompt. Then you can compare them, pick the one you like. I just showed you a step of the first one. I actually generated 5. You can see the common things of all of this, right? What it captures. First of all, the style is mostly black and white, more like a sketch rather than a colored painting. And also you can see the common features, probably like glasses, beard, and some geometric shapes appears for the glasses or for other things. And you can see some formulas here and there to represent this is a mathematician. But in general, this is very abstract. I would say, yeah, this last one especially is likely cubism. You can imagine Picasso draw this. But I would say those good examples you saw online, they probably require a bunch of trial and error for a good prompt. If you're just curious and use some prompt like I'm using here, you probably get some more Picasso style paintings. Okay. Hopefully you enjoyed today's presentation and you can have fun when you play with the Disco Diffusion yourself. I guess I won't drag anyone here anymore because we are so over time, but you are definitely welcome to talk to me about this offline. Yeah.
Okay, thank you.
Okay. Okay, thank you so much. Thank you, everyone.
Thank you.